Hi there, welcome to lecture 20 of Fox, where we're going to continue talking about expected values, because it's that important. Okay, we're going to introduce a few more sophisticated techniques that makes it much easier to compute expected values. Specifically, we're going to talk about the expected value of a sum, okay, and we're going to introduce this concept of an indicator random variable, which when used in conjunction with the expected value of a sum can make computing expected values much easier. Okay, but before we get going, let's recap what we talked about last time, which was the expected value. So the expected value is a summary now of the random variable, the entire PDF of the random variable, which itself is a summary of the complex experiment. So complex experiment, take a measurement, that's the random variable, take the expected value of the random variable, okay, and that's a mathematical formula that equates in the long run to, if you repeated the experiment many times, what would the average be? Okay, so that's the mathematical expectation. It's just a formula. We can compute it. Sometimes the computation is hard, and we did several examples. We talked about the sum of dice, the Bernoulli, the uniform, the binomial, and the waiting time. The binomial and waiting time are very important. Okay, when you try something a fixed number of times n, and you count the number of successes, or you try something where you have a certain probability of success, and you keep trying until you succeed. Okay. Then we introduce the concept of a conditional expectation, analogous to a conditional probability. Okay, so you update an expectation when new information arrives. Okay, by using the updated probability. That's not that hard. Okay, and then we talked about the law of total expectation, analogous to the law of total probability. So it makes it easier sometimes to compute an expectation by breaking it down into cases and then using the law of total expectation. What am I saying? It makes it much easier sometimes. Okay, so master the law of total expectation. Okay, so today we're going to talk about the expected value of a sum. Okay, and there are also more sophisticated techniques like iterated expectation, expected value of a product. Okay, so you can look at the textbook for those more sort of complex ideas, complex concepts. We will focus on the expected value of a sum. Okay, we'll see how we can use the expected value of a sum and the law of total expectation to do build-up expectation, and then we will introduce this concept of indicators, which together with the expected value of a sum can make computing expectations much, much easier. Okay, and so let's begin. Let's go to the board. We're going to be talking about the expected value of a sum. Okay, but before we get going, let's warm up a little by computing an expected value. Okay, and let's talk about something that you might have heard about, seen all around you, the lottery. Okay, and this thing happens, let's say, roughly every week, and the rules are that every week, let's say, you can buy a lottery ticket for $1. Okay, so it means you pick a number. Okay, and what's the number? The number you pick is a set of 5 numbers between 0 and 70. So 0 to 70, you pick 5 numbers. Okay, and you also pick the order. And now if your 5 numbers match the 5 numbers drawn at the end of every week, well, then you win. Okay, so we draw 5 numbers. Okay, and so how many possibilities are there for this outcome? So there are 71 choices for the first number, and we draw 5 numbers, so 71 raised to the power 5. Let's just say that's approximately equal to 2 billion. So the chances that your number is one of those 2 billion numbers are 1 in 2 billion. So the probability to win is 1 in 2 billion. Okay, that's pretty slim chances. Okay, now, but however, every now and again you find out that someone won the lottery. So what's going on here? It's not that you're becoming astronomically lucky. It's that many people are trying. So let's assume that there are 20 million people. Okay, and each of them buys a lottery ticket every week. Each buys a ticket every week. Okay, and if someone wins, they get whatever's in the pool. So if they lose, it goes into the pool, and some fraction of this pool is siphoned off by the state to fund public education and roads and so on and so forth. So this is a way in which states can make money. It's a government-sanctioned piece of gambling that allows people to pay a little bit of money for a big ticket payday, but at the same time it allows states to gradually generate a little bit of revenue to pay for public works projects and education and things like that. Okay, so now you have the tools to answer questions like how many weeks will it take on average for someone to win the lottery? Questions. How many weeks weeks on average for someone to win. Okay, we're ready. You have the tools to answer this question. I'm not going to answer this question. I'm just going to say that, typically when somebody wins, so the lottery has typically built up to, let's say, around 200 million. Okay, so approximately 200 million is the payday. Okay, so 2 winnings, let's say, is about 200 million. That's a little bit optimistic, but I'm just approximating here. Okay, so now if they say that that's the current, pool. Okay, and so now if you play this game, your chances of winning are 1 in 2 billion. Okay, so what are your expected winnings? Well, what's your expected gain from playing the lottery? Well, you buy a lottery ticket, you spend $1, okay, and then you win 200 million with probability 1 in 2 billion, and you win 0 with probability 1 minus 1 in 2 times 10 to the 9. So 1 minus 1 in 2 billion. Okay. So if we let a random variable x denote your winnings, so then x, denote your winnings, we can ask what is the expected value of x, okay? And it's going to equal, with probability, 1 in 2 billion, the amount of money that you have won, okay, is minus 1 for the ticket you bought plus 200 million. So it's minus 1 plus, 200 million, okay, with probability 1 over 2 times 10 to the 9, with probability 1 in 2 billion. And the amount that you have won is minus 1 with an overwhelmingly large probability, plus minus 1 with an overwhelmingly large probability of 1 minus 1 over 2 times 10 to the 9. Okay. And so we can see, okay, that your expected winnings, so this is minus 1 times, 1 in 2 billion, okay, plus minus 1 times 1 minus 1 in 2 billion. So this is equal to minus 1. So this term and this term are equal to minus 1. Okay. Plus, 200 million divided by 2 billion. So that's 1 in 10. Okay, so this is equal to minus 0.9. So your expected winnings in such a lottery are approximately minus 90 cents. Expected winnings is approximately equal to minus 90 cents. So on average, many people are playing this lottery, so on average they're all losing about minus 90 cents. So you see the state is, and where does that minus 90 cents go? It goes to the state in some sense, okay? But we won't get into the details, the fiscal details of how, lotteries are using the money and who gets the money and so on and so forth, okay? Just from your perspective, the lottery is a losing, proposition. In fact, you're losing 90 cents, for every time you play the lottery. But people still play the lottery. Why? Because, there's 90 cents. I'm losing 90 cents in change, through the holes in my pockets every week. So I might as well use that money to play the lottery, right? And why? Because the 90 cents is not really worth that much to me. But if I win the 200 million, wow, my entire life changes. Okay, so that's why people play the lottery. It's not that they don't know that on average they're losing money. It's just that, it's a little bit of money now, which I don't really care about. And if I win, it's just, it's this promise of, greatness in some sense. Okay, it's worth investing a little bit of effort if there's a promise for a big payday. Okay, now, so you get all worked up by lotteries, and you say, well, what if I played the lottery in New York and the lottery in Massachusetts? So you buy a ticket for New York and you buy a ticket for Massachusetts. Okay. And, so your total winnings, let's call it T, is equal to, let's denote by T sub New York, your winnings from New York, and T sub Massachusetts, your winnings from Massachusetts. Okay. So your total winnings is the sum of these two winnings. Okay. And so, you might think, well, whatever I win here is whatever I win here, whatever I win here is whatever I win here. These are two sort of totally independent entities. And I expect to win in total of a sum of whatever I expect to win here plus the sum of whatever I expect to win here. Intuitive. Okay, so your expected total winnings, which is expected value of t, you expect it to be, I mean, you sort of intuition suggests that these are, New York and Massachusetts has nothing to do with each other. Okay, so it should be my expected winnings in New York, okay, plus my expected winnings in Massachusetts. Okay, and so that's where we're getting towards today. So expected value of a sum. But now let me throw in a wrench. Okay, suppose you buy 2 tickets for the New York lottery. Okay, now what happens? Okay, so let's call those tickets T1 and T2. Okay, now the expected winnings for ticket 1 is 90 cents, minus 90 cents. The expected winnings for T1 is minus 90 cents. And the expected winnings for T2 is minus 90 cents. Okay, we just imagine that it's this lottery that's being played. And now you might think, well, since I bought 2 tickets, what are my expected winnings in total when the lottery is run? Okay, what are my expected total winnings? Okay. Now you think, oh my goodness, it's going to get complicated because, when one ticket wins, the other loses. You cannot win with both tickets. Okay. Whereas, in the New York and Massachusetts example, you can win with both tickets. Okay. Whereas here, if one wins, the other doesn't win, you both can't win, and so on. It looks more complicated. Okay. Because these tickets kind of depend on each other. Okay. Well, it turns out it's not any more complicated. And that's what's surprising. And that's what we're going to discuss today. Your expected total winnings, the expected total winnings is still the sum of the expected winnings. Expected value of T1 plus the expected value of T2, which is equal to minus $1.80. So if you buy 2 tickets in the same lottery, you're expecting to lose $1.80. If you buy 2 tickets in 2 different lotteries, for example, from different states, you're expecting to lose $1.80 in both cases. Okay, and so let me summarize that, and we're going to prove it. Okay, so theorem, and we'll prove it for the case of 2 random variables, but the argument holds in general. Theorem. Okay, and now this is a very important theorem, and sometimes we call it the linearity of expectation. Okay, and this is a very important theorem. Okay, and you may ask, when does it hold? Always. Okay, always. Okay. Modulo the fact that it's a finite sum. Okay, so infinite sums are tricky, but if we in both of these examples of the lotteries, our total money made is the sum of 2 things. Okay, so in general, let us define the sum of random variables. Even though I'm stating this as a theorem and I'm describing some things like the sum of random variables, and I'm going to put it all in the theorem just so that it's all in one place. So define the sum of random variables. As follows. Okay. So let's say you have random variables x1 and x2. x1 and x2 are random variables. Okay. Then we can define a new random variable. Define a new random variable. New random variable x, which is, let's call it, a1 x1 plus a2 x2. Okay, and you say, what? I measured temperature and pressure and I'm taking the sum? Okay, because remember, random variables were measurements. So now we need to go back to the formal definition of what it means to be a random variable. So a random variable is a function, x1 is a function that maps, my outcome space to the real numbers. And x2 is a function that maps my random variables to the real numbers. Okay, so we can talk of x1, taking as input some outcome and outputting a real number. Okay, and x2 as taking some outcome and outputting a real number. Okay, so this is where it's very important to realize that a random variable has a very formal definition as a function from the sample space to the real numbers. Okay, and I can take the sum of two functions. I can define a new function, which is the sum of two functions. So x of w. So x is a new random variable. It's a function that maps my sample space to the real numbers. And I'm going to now define it for you. Okay, x, when it sees the outcome w, simply outputs a1 x1 of w plus a2 x2 of w. And now that's very well defined. So basically, I'm defining a new function as the sum of two functions. Okay? And we've seen this many times. You can define functions in terms of other functions. That's what it means to take a sum of random variables. Okay. So even though I'm defining this sort of peripheral stuff inside the theorem, it's useful to have it inside the theorem so that you know what a sum of random variables is. So now what does the theorem say? The theorem says that the expected value of x, okay, is equal to the expected value of a1 x1 plus a2 x2, okay, which is equal to a1 times the expected value of x1 plus a2 times the expected value of x2. Okay, so now we say that this is a linear combination of x1 and x2, and the expected value of a linear combination is that linear combination of expected values. Okay. In particular, the expected value of a sum is equal to the sum of expected values. So when a1 and a2 are both 1, it's equal to the sum of the expected values. Okay, and that's very important. Now, because the expected value of a linear combination is that same linear combination of expected values, this is called the linearity of expectation. So that's the theorem, okay? Or in words, okay? An expected value of sum is equals sum of expected values. The expected value of a sum is the sum of expected values. That's poetry. Memorize it. The expected value of a sum is the sum of expected values. The expected value of a sum is the sum of expected values. Put it in your head and keep it there forever. Okay. Now, mathematically, what this means is that you can take an expectation into a sum or pull it out of a sum. Okay. So constants, okay, and addition can be taken outside an expected value. Okay, and you might ask, what the heck does that mean? Because look, here we have constants and an addition inside an expected value. And now I've taken the constants outside, and I've also taken the addition outside. Okay? And if you think back, when we did summation, we had the constant rule and the addition rule. Okay? And that's exactly what is going on here. That, a constant can be pulled out. So an expected value is like a sum. Not like a sum. Remember, we defined it last time. It is a sum. So an expected value is a sum. And essentially what's going on here are the constant and addition rules for summation. That you can pull a constant outside of an expected value because an expected value is a sum. And you can take the expected value of terms added together as the addition of those individual terms. So these are exactly the rules that we had for computing summation. Now we are seeing them again when we're computing expected values of sums, and that's because the expected value is a sum. So let's prove this. Okay, so proof. Okay, now we'll use the sample space, version of the expected value, which I asked you to sort of convince yourself of from last lecture. So what is the expected value of a random variable x? 1. Okay, it's the sum over your outcomes in your sample space, okay, of, the value times the probability of the value. Okay, that's what the expected value is. Okay. It's a little bit easier to work with the definition of the expected value through the sample space because all the random variables are defined on the same sample space. But the random variables may take on different values. But they're all functions defined on the same sample space. The expected value of x2 is equal to the sum over your outcomes, the value of the outcome, i.e. the measurement, this is x1 and this is x2, the value of the outcome times the probability of the outcome. Okay, and the expected value of x is equal to the expected value, the sum over outcomes, x of w, p of w. Okay, but now this is where the definition of the sum, this function which is the sum, comes into play. So this x of w is this linear combination. So this is equal to the sum over your outcomes of a1 x1 of w plus a2 x2 of w times p of w. Okay? And where's that coming from? X of w, we defined it here. We defined what it meant to be the sum of random variables. Okay, but now it's straightforward use of the rules for summations. Okay, so this is equal to the sum of, we can multiply the p of w. So there are actually two terms here, a1 x1p, a2 x2p. Okay, and we're taking a summation of two terms added together. So, the addition rule says that this is the sum from over w in omega of a1 x1 of wp of omega plus the sum over omega in your sample space a2 x2 of omega p of omega, and this is the addition rule for sums. Okay, and now I can apply the constant rule. I pull out the a1, I pull out the a2 from the sums. Okay, so this is equal to a1, the sum over outcomes in my sample space x1 of the outcome, p of the outcome, the probability of the outcome. So this is an expected value plus, a2, I pulled out the constant a2, sum over my outcomes, x2 of the outcome, p of the outcome. Okay, but now I see here I have the expected value of x1, and now I see here I have the expected value of x2. So this is just equal to a1 times the expected value of x1 plus a2 times the expected value of x2. And that's the end of the proof. Okay, it's a very short proof. It's exactly, analogous to the constant and addition rules from when we computed sums. Okay, and now, let me just point out that when you look at this proof, you'll see that it'll hold no matter how many terms are in the sum. So, I can just apply the addition rule for if I have k terms in the sum. So if I take the sum of k random variables, I'll just have k terms in the sum. So I'll have, k terms added together. So I can break them all apart and get individual sums, and then I'll get individual expectations. Okay. So this easily extends to more than two random variables, to sums, to a sum of more than two random variables. Okay, and so there's the proof of this very fundamental result, and I'm going to state it again because it's poetry and you should memorize it. The expected value of a sum is a sum of expected values. The expected value of a sum is a sum of expected values. And there's the more complicated version, which just says that, it also works if you have constants multiplying the random variables before you take the sum. Okay, so that's called the linearity of expectation. Slightly more sophisticated version, but the more basic version, the expected value of a sum is a sum of expected values.
memorize that. Here's the proof. Now let's do hordes and hordes of examples. Okay? Just to show you how this makes life so much easier when it comes to computing expected values. And why is it so important to compute expected values? Because you've done this complicated experiment. Okay? This complicated experiment has a complex outcome. Okay? We're not interested in the complex outcome, so we summarize of a measurement in a random variable, a function from the outcome to a number. Okay? So we've summarized the experiment in a random variable, and now we are still, looking at the random variable and its entire PDF and saying, it's too complicated. Can you give me one number which summarizes the experiment? That's the expected value. Okay? In some sense, it's what you expect to happen. Okay? It's the expected measurement. In a more formal sense, if you repeated the experiment many times, okay, the expected value is what you will see on average. Okay? If you take the average of the values that you measure. Okay, so expected value is important. Okay, and now we just see that if you have a sum, it's almost as easy as just computing the individual expected values. Let's do examples. Let's erase. Do examples. Bam, bam. Let's knock down example after example after example. Whew.